Hello. In this video, I'd like to talk about changes of physical states of matter as described in Chapter 10.4 in your textbook. Let's begin with a really important concept in all of science, and that is equilibrium. Equilibrium is defined as a dynamic condition in which two opposing changes occur at equal rates in a closed system. So we have a system in which two opposite things are happening, one in the forward direction and one in the reverse direction, but because they are happening at the same rate, it appears that nothing is changing. I'll give some examples of this in class, but let's move on and talk about something that's relevant right now. Let's consider a volatile liquid in a closed container. Well, what does it mean to say that a liquid is volatile? Well, that basically means it has a tendency to evaporate. It can easily go from the liquid phase to the gas phase. Okay? So when we begin, we've got nothing but liquid at the bottom, and we've got vacuum at the top. As time progresses, some of the liquid particles escape and move into the gas phase, as indicated by the upward arrows. After a while, the number of particles in the gas phase increases to the point where now the reverse process begins to occur. That is, liquid particles begin to condense and go back to the liquid phase. And at that point, the rate of evaporation is equal to the rate of condensation, and we call that state vapor equilibrium. So vapor equilibrium occurs when the rate at which the liquid particles are escaping and evaporating into the gas phase is equal to the rate at which the particles in the gas phase condense to reform the liquid. The equilibrium vapor pressure is defined as the pressure exerted by the vapor in equilibrium with the liquid at a given temperature. So if I were to actually measure the pressure exerted by the gas particles up here when it's at equilibrium, that pressure would be the equilibrium vapor pressure. Now, how do you suppose that equilibrium vapor pressure varies with temperature, and why? What would happen to the pressure exerted by the vapor above and the far right as we increase the temperature? Well, as you might expect, as the temperature increases, the kinetic energy of the molecules in the liquid phase would begin to increase, and therefore the molecules would start to move faster. As they began to move faster, a greater fraction of the molecules would have sufficient kinetic energy to overcome whatever the intermolecular attractive forces are that are holding the molecules together and escape and go from the liquid to the gas phase. Therefore, there would be more molecules in the gas phase, and as a result, we would have higher vapor pressure. So it is always the case that the equilibrium vapor pressure of a liquid increases as temperature increases. We deal with that quantitatively in AP Chemistry, but for now we're just going to think about it qualitatively. And I'm going to show you a graph that illustrates how the vapor pressure of three different liquids varies with temperature. It's kind of a complicated graph. There's a lot going on, but I'll explain it in detail. And this is what it looks like. I've got temperature as the independent variable in degrees Celsius. I've got vapor pressure in units of torr, which we'll explain soon, on the y-axis as the dependent variable. And there are three lines, one in green, one in red, one in blue. The green line represents a substance called diethyl ether. The blue line represents a different substance called water, and the red line represents a different substance, ethanol. And as you can see, for each of these three liquids, as the temperature increases, the vapor pressure increases, and it's actually an exponential increase. But you'll notice that the three different substances have very different vapor pressures. At any given temperature, diethyl ether will have the highest vapor pressure, followed by ethanol, and water will have the lowest pressure. Why is that? Well, we'll talk about that on the next slide. I'll also point out that there is a particular pressure indicated on this, which is a pressure of 760 torr, which corresponds to atmospheric pressure. And you'll see that there are very specific temperatures at which these liquids have that particular vapor pressure, which I'll get to in a bit. So, what happens when the vapor pressure is equal to atmospheric pressure? Well, at this point, the escaping tendency of the particles, indicated by the red arrows pointing upward, is equal to the atmospheric pressure, and that temperature is called the normal boiling point. The normal boiling point is the temperature at which the vapor pressure of the liquid is equal to atmospheric pressure. And this is the temperature at which the liquid spontaneously evaporates. What about the temperature at which the vapor spontaneously condenses? Well, that would be essentially the same. So the boiling point of a liquid is equal to what you might call the condensation point. The temperature is the same, it's just a matter of which direction you're going. Now, let's ask ourselves, how does the boiling point depend upon the molecular structure? Here again are the three molecules that we looked at in the graph. Diethyl ether, which has a boiling point of 34.5 degrees Celsius, ethanol, 78.5, and water, 100.0. Here is the Lewis structure for diethyl ether. You can see in the center there is an oxygen atom with two lone pairs and two bonds. Therefore, it would have a bent geometry. Therefore, the molecule would be polar, and the most important intermolecular attractive forces would be dipole-dipole forces. Ethanol looks very similar, except now the oxygen, which also has a bent geometry, has an OH bond. That means that while the molecule is polar, the most important intermolecular attractive force is hydrogen bonding. Water, of course, has two OH bonds. The bent geometry means that it is, of course, polar as well, but because it has two OH bonds, it can undergo lots of hydrogen bonding. So what we can see is that as we go down from top to bottom, the strength of the intermolecular attractive force is increasing, and therefore the boiling point increases as well. So to summarize, we can say that when we have stronger intermolecular attractive forces, there is more energy required to separate the molecules, and therefore there is a higher boiling point. Well, how much energy is that? We can actually measure for any given substance what's called the molar enthalpy of vaporization. Enthalpy is just a fancy word that means heat, and it is symbolized by the uppercase letter H. Delta H sub V means the change in enthalpy required for substance to vaporize. The definition is the heat energy required to vaporize 1 mole of the liquid at its boiling point in units of kilojoules per mole. Now, how do we suppose the molar enthalpies of vaporization of these three liquids will vary? Here are the names and the formulas. Here are the boiling points. Well, as you might expect, as the strength of intermolecular attractive forces increases, and therefore the boiling point increases, you would predict that the molar enthalpy of vaporization would increase as well. For diethyl ether, that's 27.5 kilojoules per mole. For ethanol, 38.7 kilojoules per mole. And for water, 40.7 kilojoules per mole. So we see a general trend here. As the intermolecular attractive forces between the molecules in the liquid phase increase, the amount of energy required to separate the molecules, as measured by the molar enthalpy of vaporization, increases, and as a result, the temperature required to evaporate it increases as well. Now, we can use molar enthalpy of vaporization as a conversion factor for a kind of interesting quantitative problem. So, here's a question we can ask. How much heat energy would we need to evaporate 100.0 grams of ethanol? So I've got this substance for which I know the molar enthalpy of vaporization. Okay, we said before it was 34.7 kilojoules per mole, and I want to evaporate 100 grams of ethanol. Well, let's do a little roadmap here. We can start with the mass of ethanol, of course, because the molar enthalpy of vaporization is in kilojoules per mole. The first thing we have to do is convert that to moles of ethanol, which of course we know how to do, and then we can use, so that would be dividing that by, that would be dividing that by the molar mass, and then we would use the molar enthalpy of vaporization as our conversion factor to convert from moles of ethanol to amount of heat energy. Obviously, we'll begin by calculating the molar mass of ethanol, and now let's do our calculation. So we'll start with 100.0 grams of ethanol, divide that by the molar mass, 46.07 grams per mole, so that grams cancel and we're left with moles. And then we'll simply multiply by the molar enthalpy of vaporization, which once again is 38.7 kilojoules per mole of ethanol. Moles of ethanol cancel, and we are left with a value of 84.0 kilojoules of energy. So if I wanted to evaporate 100 grams of ethanol, it would take 84.0 kilojoules. Well, you may not have a good sense as to how much a kilojoule is, so I looked on a candy bar wrapper, and I saw that one Snickers bar has 1,050 kilojoules of energy in it, so that's about 12 times the molar enthalpy of vaporization of ethanol. Now, let's think about another phase change. Suppose I have a sample of water and I want to start removing heat energy from it. So I cool it, and in the process, what happens when I remove heat energy? Well, of course, obviously it's going to freeze, and if I start with liquid water, I'll end up with a bunch of ice cubes. Freezing is the physical change of a liquid to a solid, and in doing so we must remove energy. The opposite, melting, is the physical change of a solid to a liquid, and for that we have to add heat energy to go from the solid to the liquid. What do we call the temperature at which they're in equilibrium? That would be called the melting point. The melting point is defined as the temperature at which the rate of melting is equal to the rate of freezing, and of course the freezing point is the same thing. We can also talk about the heat energy required for this particular physical transformation, and that's called the molar enthalpy of fusion. Fusion simply refers to melting or freezing. And the molar enthalpy of fusion is defined as the heat energy required to melt 1 mole of solid at atmospheric pressure in, again, units of kilojoules per mole. So let's do a problem now. Instead of using the molar enthalpy of fusion the way we use the molar enthalpy of vaporization, let's see how we could calculate the molar enthalpy of fusion. So let's say I do an experiment in which I find that I have to add 10,600 joules of heat energy to melt 100 grams of frozen ethanol in order to turn it from the solid to the liquid. How can I use that to calculate the molar heat of fusion of ethanol? Well, the molar heat of fusion is simply the amount of heat energy required to completely melt or freeze 1 mole of the substance. So I think what we need to do is to convert our heat energy from joules to kilojoules, and then convert our grams to moles, and that should get us what we need. So in the numerator here, I'm going to begin by taking my 10,600 joules and convert that to kilojoules by multiplying by 1 kilojoule per 1,000 joules, because kilo means 1,000. I'll divide that by my 100 grams of ethanol, but to convert that into moles, I'll divide by the molar mass, or multiply by 1 mole, or over 46.07 grams. So grams of ethanol cancel grams of ethanol, joules cancel joules, and I'm left with a value for the molar enthalpy of fusion of ethanol of 4.88 kilojoules per mole. So this represents the amount of heat energy needed to melt 1 mole of frozen ethanol. Now, in class, I'm going to do a fairly cool demonstration in which I take a sample of iodine, which is a dark black-purple crystalline material. I'm going to place it in the bottom of a beaker, cover it with a watch glass, and add heat energy. And what you will see is something fairly cool. The solid iodine will disappear. You will see iodine vapor in the gas phase. And eventually, you will begin to see iodine crystals begin to form on the watch glass in the top of the beaker. What we observe is a process called sublimation. Sublimation is defined as the change of state when you go directly to the gas phase from the solid phase. The opposite process is called deposition. That is the change of state from the gas directly to a solid. So you will observe the iodine subliming as it goes from the solid into the gas phase, and then you will see it deposit on the sides of the beaker. And at the sublimation temperature, the solid and gas phases are in equilibrium. So let's summarize and list by name the changes of state. From solid to liquid, that of course is called melting. From liquid to solid is freezing. From gas to liquid is evaporation. And from liquid to gas is condensation. And finally, from gas to solid is sublimation. And from solid to gas, from solid to gas is sublimation. And from gas to solid is deposition. And that pretty much covers what we need to know about phase changes.